Hello and welcome to the screencast. My name is Vijay Kumar and I'm going to show you in this video how to use the PS09 evaluation software. After you have successfully installed the PS09 evaluation software, you can launch the software from the Start menu. There are 9 tabs or sheets in the evaluation software. I will go through each of these sheets and will explain the various configurations on them. Before we go into the sheets in detail, it would be useful to know that some areas on all the sheets have a blue background. These areas contain the most important configurations and it is sufficient to concentrate on them at first. We will start with the setup sheet. It is the startup page of the evaluation software. If the PS09 hardware is already connected to your system, on opening the evaluation software, you will see an identifier here with 100F. This is an ID specific to the PS09. Let us go to the other buttons on the sheet in detail. First is the Power On Reset button. Clicking this button sends a reset to the PS09 chip. All the configuration registers are restored to their reset state. Next is the Download Configuration button. Clicking this button will download the configuration from the evaluation software into the configuration RAM on the PS09 chip, that is, from address 48 to 63. Next is the Init Reset button. It will send a partial reset to the PS09, that is, the configuration is retained but the DSP is stopped. No measurement or processing is done further. Next, we will see the interface selection box. The PS09 chip can communicate either through the SPI interface or the I2C interface. This selection of the interface is done here. The evaluation software by default comes up in the SPI mode. You can verify if the communication is working fine by clicking on the Verify Interface button. This message window shows an OK status if the communication is positive. You can switch to the I2C communication mode by clicking here. The evaluation software wants you to set your hardware accordingly to I2C. You can once again verify the communication through the I2C interface by clicking on the Verify Interface button. The message shown here is also positive. Further, you see here the Save Config button. If you configured the PS09 through the evaluation software to a good working configuration, you might want to save the settings of the evaluation software for future use. This can be done by clicking on this button. You can enter a file name for your configuration file. In my case, myconfig, and the file is saved. A saved configuration can be reloaded in future by clicking on the Load Config button. You can then select the configuration file and all the settings in the evaluation software are updated from this file. On the right, you see the contents of all the configuration registers that will be downloaded into the PS09. Once a configuration is set, you can use the same in your application program, which you can develop using the PS09 assembler. This window's contents can be copied and pasted directly into your configuration file in the PS09 assembler. Now, there are some ready-to-use configurations that the evaluation software offers. OIML 3000 low cost is a working configuration for the LC or low cost module. OIML 6000 high resolution is a working configuration for the HR or the high resolution module. Wheatstone configuration is a working configuration for the Wheatstone module. You can load any of these ready-made configurations depending on the plug-in module in your hardware and then press the Download Configuration button. The PS09 chip is now configured and is ready for measurement. Now let us see the measurement sheet. This sheet shows all the measurement results from the PS09. This includes the individual half-bridge measurement results, the temperature measurement results, and also the raw measurement results of the time to digital converter, the TDC, in the PS09 chip. In this part of the sheet, you can set the full scale of display depending on the full scale capacity of your load cell. For example, if you're going to measure using a 10 kilogram load cell, you enter the value 10,000 here. If you know the sensitivity of your load cell, you can set it here. For example, for a load cell with sensitivity of 2 millivolt per volt, enter the value 2 here. Depending on the settings in the above two boxes, the scaling factor is automatically filled. The mult-HB multiplication factors for the 4 half bridges are set on the ALU page. The average of the 4 multiplication factors is taken here automatically, and the software multiplication factor is calculated. If you're programming the PS09 using the assembler for this load cell, then use this software multiplication factor for scaling your result. You can set the minimum step size for measurement here. Please note that all the settings done in this area are purely only for the evaluation software. They have no effects on the chip's configuration itself. With these settings, the result read from the PS09 chip can be interpreted more easily. Once you have set the correct configurations for measurement, for example, by loading a ready-to-use configuration from here, for example, you can start the measurement by clicking on the Start Measurement button. The overall measurement result, that is the consolidated HB0 result, can be read from this field here. The standard deviation in the read out measurement value and the resolution of the measurement in bits can be read out here. The resolution in bits displayed here is calculated according to the sensitivity of the load cell. Higher the sensitivity, better will be the resolution. When this option 0 offset is set, then the offset of the load cell is set to 0. If this option is not set, then the actual offset of the load cell can be seen here. The TARA option in an actual weighing scale is the equivalent of the 0 offset option. During the measurement, you can calculate the current offset of the load cell by clicking on the Calculate Offset button. You can set the number of offset values that have to be averaged to get the current offset value here. The measurement results from the PS09 can be filtered in the evaluation software using a median filter or a sync filter. The length of the filter is selectable here. Down here, you can read the TDC1 and TDC2 measurement results respectively. These are actually the discharge time measurements through each half bridge shown here in nanoseconds. The discharge time usually lies in the range of 70 to 150 microseconds. You can check if the system is working correctly by checking if the discharge time shown here is in accordance with the discharge time that you designed for. You can read the value of the supply voltage currently being measured by the PS09 from this box here. You can disable or enable the evaluation software from reading this result by clicking on this box. In this part of the measurement sheet, you can perform the settings for the temperature measurement in PS09 and also see the results. The temperature measurement can be enabled by clicking on this box here. This sets the appropriate configuration register bit setting to enable. The value of the internal temperature measurement resistor, RTemp, can be selected to 300 ohm or 600 ohm depending on the value of the strain gauge resistor connected in your system. For example, if you have a 350 ohm load cell, select 300 ohm. If you have a 1 kilo ohm load cell, select 600 ohm. The temperature coefficient of resistance of the internal temperature measurement resistor is specified as 3700 ppm per Kelvin typically, with a variation of plus or minus 5% from chip to chip. Leave the default settings unchanged in this box. For more details on the significance of this value, please refer to the PS09 datasheet. The temperature coefficient of resistance TK-res of the combination of the strain gauge resistor and the internal temperature measurement resistor is shown here as TK-res. For a nominal current temperature entered here, this resultant TK-res is calculated once. Once you press the Start Measurement button, all the measurement values in this sheet are updated regularly. Pressing the Calculate TK button will calculate the TK-res here. To demonstrate a measurement with a working configuration, press Start Measurement. The 0 offset is selected, hence the measurement is around the 0 value. Placing a load shows the respective measurement value. Next, we will see the graphic sheet. As the name implies, this sheet displays all the measurement results graphically. Again, the individual half-bridge measurement results HB1 to 4, the consolidated measurement result HB0, and the temperature measurement result can be displayed here on this sheet. You can select which result ought to be displayed using the drop-down boxes here. You can start the measurement from this sheet by clicking on the Start Measurement button here. The software shows the measurement values read out from the chip graphically. The measurement rate depends on the measurement configuration in the PS09 chip. You can read out the measurement rate from the front-end sheet. The actual measurement frequency shown on the front-end sheet is 5.1 Hz. This corresponds to approximately 0.2 seconds. This means a new measurement sample is read out every 0.2 seconds. The scale on the x-axis is the number of samples taken over time. On the y-axis is the amplitude of the measurement value. You need not read out every measurement value. Instead, you can select to read, say for example, only every 10th measurement value. You can set this here. This function is particularly useful when you want to observe the measurement over a longer period of time, like for example, while studying noise or signal quality. Once the measurement has been performed for a definite time duration, you can save the measurement results in a file. First, stop the measurement by clicking on Stop. Then click on the Save Data to File button. You have to enter a file name, for example, my data, and the file is saved. Once saved, you can open the file in future using any text editor. The file format looks like this. The content shown here in the right panel are the same as that shown on the measurement sheet. Next comes the front-end sheet. The settings on this sheet are very important as they mainly determine the measurement configuration in PS09. All the settings on this sheet translate into configuration register bit settings in the PS09 chip. Depending on the strain gauge connected to your hardware, you can select the number of half bridges here. The number of fake measurements is configurable from this drop-down box. The enable or disable for the Wheatstone mode is done through this checkbox here. The measuring range of the TDC in the PS09 chip, measuring range 1 or 2, is selectable here. By default, it is measuring range 2. The cycle time, which is the sum of the discharging and the charging time, can be set here. In other words, it is the time interval between two consecutive discharge times, and it depends on the strain gauge resistance and the load capacitor. The discharge time is typically around 90 to 150 microseconds. The charging constitutes about 30% of the cycle time and must be long enough to allow the load capacitor to charge completely. If the cycle time is too small, there occurs an overflow that is indicated on the measurement sheet. You can set the cycle time in multiples of 2 microseconds or 100 microseconds. For continuous measurement mode, it is set in multiples of 2 microseconds. The number of discharging cycles needed to make a complete ratio measurement depends on the setting of the number of bridges. Each half bridge contributes to 2 cycles of measurement. Thus, a full bridge needs 4 cycles and a quattro bridge needs 8. The number of times this complete measurement ratio has to be measured to calculate one measurement value is given by the setting of the averaging rate configured here. The conversion time and the maximum allowed measuring rate are updated here automatically. In addition, depending on the setting of the MFAKE, 2, 4 or 8 dummy measurements are made at the end of every measurement cycle. This is in continuous measurement mode. You can configure the single conversion measurement mode by setting the checkbox Single Conversion here. The value of the single conversion counter in configuration register 0 can be set here. You can see here that the actual measuring rate is reduced in single conversion mode automatically. The third measurement mode, described as the stretched mode in the PS09 datasheet, can be configured here. Here it is called the pulsed mode. Once the stretched mode is selected, the cycle time is automatically set in multiples of 100 microseconds. The control of the 4 MHz external oscillator can be done here. If it needs to be switched off or switched on permanently, or you can also set the delay between the start of the oscillator and the start of the measurement to 100, 200, 300 or 400 microseconds. On the left here, you can perform all settings that are necessary for the comparator. The running duration of the comparator, the selection between the internal and the external comparator, the value of the working resistor in the internal comparator, and the option to select a higher comparator threshold. All these parameters can be configured here. The next sheet in the evaluation software is the ALU page. Here you can configure the multiplication factors for each of the 4 half bridges, mult HB1 to mult HB4. This value can be in the range of -8 to +7.999999. On this sheet, you can configure the gain correction over supply voltage variation using this option. The multiplication factor mult UB can be set here. You can enable the gain compensation for the temperature behavior of the electronics by setting this bit here. The correction factor itself can be set here. The factors that are used for correction of the gain and offset drift of the whole system over temperature, namely the Tk gain and Tk offset, are to be set here. The enable bit to enable the temperature compensation and correction is the mod R-span bit here. If the temperature compensation is to be performed with the integrated R-span resistor in PS09, that is RTEM, then the internal R-span bit is to be set. On the right side of the sheet are settings for execution options for the user code. Select this option if the configuration in the OTP or external EEPROM has to be used after a power-on reset. Select this option if a user-written power-on reset code has to be executed after a reset. Select this option if a user code has to be executed after every measurement completion, or if in sleep mode, then on every wake up. The last options on this tab pertain to the DSP interrupt. Here you can select the source pin for the interrupt, the polarity, that is the triggering edge of the interrupt, and finally enable or disable the interrupt to the DSP. Next is the experts page. Most of the settings on this page are mainly intended only for special applications. It is strongly recommended to consult the support team at ACAM before you change the settings on this page. Hence, I will explain to you only those settings on this page that you as a user are most likely to use. Here you can see the trim bits for tuning the internal 10 kHz oscillator. In normal cases, please do not alter the settings of these bits. However, when you are driving an external LCD controller with the LCD clock from PS09, then you might need to adjust these trim bits to get the required LCD clock frequency. Here are the options to select the RC oscillators 1 and 2. For the low cost or LC modules, you have to select Cell RC OS1 option for the module to work. Here is the option to configure different pulse widths for the external LCD driver clock. This LCD clock pole option helps to configure the polarity of the LCD clock. Finally, here is this TDC sleep mode. Setting this bit disables any actual measurements, but all tasks that are carried out at the end of a measurement are performed. Please note that this can be used only in conjunction with the single conversion measurement mode. Now we will see the memory page of the evaluation software. It shows the 4 major memory areas of the PS09 chip: the RAM, data or internal EEPROM, the OTP and the external EEPROM. Let's start with the RAM. Here we can read and write to any address in the RAM address space in the PS09 from 0 to 255. While entering the address or the data, you can opt to enter the same as either a decimal or hexadecimal or binary or octal number. You can set a RAM address, for example 10, type in a value, for example AB, and the value can be written to the RAM by pressing the right button. You can read the content at the selected RAM address by pressing the read button. The content is displayed here. As you can see, the content is displayed byte-wise in these 3 boxes in decimal only. However, you can select if the value has to be displayed in any other base here. The 3 bytes of the RAM content are displayed in 3 separate boxes. The power reset, init reset, start TDC cycle and start new cycle buttons are present here for quick and easy access. Next is the internal or data EEPROM. The EEPROM ought to be enabled before reading or writing to it. Additionally, the band gap voltage has to be switched on before writing to the EEPROM. However, when you press the read button, the EEPROM is enabled automatically. The address to be read can be set here. Here again, you can choose to enter the values in decimal or hexadecimal or any other radix. Before writing to an address in the EEPROM, that address has to be erased by clicking on the erase button. Then you can feed in a value, for example CD, and write the value to the address by clicking on the right button. The value can be read back here. You can also erase the entire EEPROM by using the block erase button. And you can write the entire EEPROM with the same data byte using the block write button. Once you've completed reading or writing to or from the data EEPROM, you have to manually disable the EEPROM by pressing the EEPROM disable button and switch off the band gap voltage by pressing the B gap off button. You can select the access time to the data EEPROM in this drop-down box here. The next memory area on this sheet is the OTP. Please keep in mind that once an OTP address is programmed, it cannot be reprogrammed. Hence, take care not to write in arbitrary values into the OTP. You can read from an address in the OTP by pressing the read button. The OTP enable on is automatically enabled when you read from the OTP. Before writing to an address in the OTP has to be enabled. The voltage to the OTP has to be switched on and the OTP program signal has to be turned on. You can then type in the data for the OTP, for example 32, and write it to the OTP address set here by using the write button. You can access the entire 8 KB of OTP memory through the evaluation software. The address high is the block address and the address low is the actual address inside the block. Each block consists of 256 addresses and there are totally 32 blocks. For example, if you want to read address 258, it is the third byte in the second block. Therefore, you have to set the block address to 1 and the address low to 2 and perform a read. Therefore, corresponding to 8 KB, there are 0 to 31 blocks, each with bytes 0 to 255. The final memory area is the external EEPROM. The access speed to the external EEPROM can have 4 possible settings selectable here. It is by default set to fast. Similar to the OTP part, the address high corresponds to the block address and the address low corresponds to the actual address inside the block. Hence, block address can be a maximum of 31 and address low a maximum of 255. You can read and write to the external EEPROM by clicking on these buttons. Sometimes, it might be necessary to erase some bytes of data if the chip is already programmed, especially the configuration area of the external EEPROM. You can erase any selectable number of bytes from these boxes and then by pressing the erase button. By default, the setting is 48 bytes, so only the 48 configuration bytes are erased. You can erase a maximum of 255 bytes in one go. This is block 0. To erase higher blocks, set the block address here. There is a small field on this page that pertains to sending single commands to the PS09 through the SPI or I2C interface. You can enter the command or value here and press on the Send Byte to PS09 button. In SPI mode, you can also send a single pulse on the SPI chip select by pressing on the Send SSN Only button. Next is the I/O interfaces page. On this page, you can configure the multi-input keys, the capacitive keys, the UART, and the 8 general-purpose input-output ports or GPIOs in short. First, we will see how the GPIO ports are configured. Each GPIO pin can be configured as input or output or input with pull-up or pull-down. These 4 possible configurations can be simply selected in the drop-down box here. When a pin is configured as input, additionally, the respective digital input buffer has to be enabled. These pertain to the settings of bits 23 to 16 in configuration register 11. For example, if GPIO 7 is configured as input, additionally, the 7th bit corresponding to GPIO 7 has to be set to 1. When a pin is configured as output, the state of the output pin is controlled by the respective bit in this box. For example, if GPIO 6 is configured as output and if the state of the bit should be 1, then this box here is set to 40 hex. If the bit should be set to 0, then this box must be set to 0. There are 2 I/O pins in the PS09 used for diagnostic functions, namely the GPIO 3 and 4. The various possible diagnostic functions on GPIO 4 can be selected from this drop-down box here. For example, selecting UART-TXD will map the transmit output of the UART module in the PS09 onto the GPIO 4 pin. Please remember that you have to additionally configure the pin itself as input or output depending on the diagnostic function you choose. This box is similarly for selecting the functionalities on GPIO 3. As you can already see here, the pins 3, 4 and 6 are labeled as multi-in 1, 2 and 3. This means that you can connect multi-input keys using resistors on these 3 pins. Please refer to the PS09 datasheet for how to exactly connect the keys. Now we call each of these pins as multi-input port. Now on each multi-input port you can connect up to a maximum of 8 keys. Thus for 3 multi-input ports you can connect up to 24 keys. On the PS09 evaluation board, however, there are only 8 keys connected across 3 multi-input ports. 2 keys on multi-input 1, 2 on multi-input 2 and 4 keys on multi-input 3. To configure a multi-input pin, first enable the multi-input pin, then configure the pin as input, next ensure that the digital input buffer on that pin is switched off. Select the scanning frequency for the keys by selecting these 2 options accordingly. Now the key is ready to use. You can see that when the configured key is pressed on the evaluation board, the respective key in the key matrix shown here will glow in light green. Additionally, you can notice that the status register that shows the state of the pressed keys is also updated here. Next, we will see how to use the capacitive keys. There are 4 capacitive keys connected to the PS09 evaluation board. They are called C port 1, 2, 3 and 4. They are connected to GPIOs 3, 4, 5 and 6 respectively and can be individually enabled or disabled. The reference capacitor Cref is connected to GPIO 7. To configure a capacitive key, first enable the capacitive port, then configure the respective GPIO pin as input. Please make sure you also configure the GPIO 7 as input. Ensure that the digital input buffer on that pin is switched off. Select the scanning frequency, either 39 Hz or 78 Hz here. Then you can choose for automatic threshold adaptation by setting this option to 1. In this case, the threshold to sense a capacitive key is automatically tracked and adapted by the chip. You can also set a fixed threshold by setting this option to 0. Then you have to set the threshold for each pair of capacitive ports here. Then select the value of the internal discharging resistor here depending on your capacitive switch values and the Cref values. Once configured, you can see that pressing the capacitive key shows a change in the ratio measured by the chip. This is depicted here graphically. C1, C2, C3, C4. Finally, here is the configuration for the UART. The UART can be enabled or disabled by setting this option. When enabled, then the software allows you to configure the other UART settings. For transmitting with the UART, select the UART clock enable. It enables the global clock to the UART module in the chip. Then select the baud rate here. Select the mode. Select or deselect the 4 MHz clock depending on whether you're using a 4 MHz oscillator or 3.68 MHz oscillator. Depending on the clock, the baud rate will be generated accordingly. Then select the GPIO pin which has to be used as transmit output. You can either choose GPIO 4 by selecting the UART-TXT option from here, or select GPIO 3 by selecting the same option from here. However, on the evaluation board, transmission is possible only through GPIO 4. Hence, select the UART-TXT option in the Mult-IO 4 cell. Then, Configure the GPIO4 as an output so that bytes can be sent out from the chip on GPIO4 pin. Select the parity. Select the number of bytes to be sent, for example 2. Then enter the bytes in RAM address 86 onwards, 3 bytes at each address. This has to be done on the memory sheet. At RAM address 86, the data entered is ABCD. CD will be the first byte to be sent. AB will be the second byte to be sent. Then select the UART trans option once and deselect it. This will generate the start transmission pulse and the 2 bytes are sent out in one go. You can recognize that the bytes have been transmitted by reading the UART register 80. Here you can see that bit 9 is set, that is, the transmit interrupt is set, which indicates the completion of transmission. Similarly, you can send up to 16 bytes in one go by setting the byte count here to 16 and then filling the bytes from RAM address 86 onwards. To receive using the UART, the same configurations as for transmit are valid. Additionally, the GPIO pin which has to be used as receive input has to be selected in this option here. On the evaluation board, reception only through GPIO 5 is possible. Hence, set this option to 3. Then, configure the GPIO 5 as an input so that bytes on GPIO 5 can be received in the chip. Enable the digital input on GPIO 5 by setting this option here to hex 20. Finally, set the UART receive enable. When a byte is received on the GPIO 5 pin, it can be read out from RAM address 80, the lower 8 bits. The final sheet is the temperature compensation sheet. This sheet is used for performing gain and offset compensation of load cells and finally evaluating the TK gain and TK offset parameters. There is a dedicated screencast by the name Temperature Compensation of Load Cells that explains how to use the parameters on this sheet. With this, we come to the end of the screencast. Thank you for watching. Here are some links that offer you more information regarding our products. Thank you once again and goodbye.